Hello dear students. Now we will move on to section 2.6 in which we will study about the Lagrange method. Now this method is used to solve only quasi-linear PDEs, and in this method we will get a general solution of the PDE. General solution means it will involve an arbitrary function. So such solutions are called general solutions. So when you solve a PDE by Lagrange method, you will get a general solution of the PDE. And the main drawback of this method is that it does not depend upon the initial data. So we will see how to do problems using Lagrange method for solving a quasi-linear partial differential equation. So consider our standard type of quasi-linear PDE, which is a ux plus b uy equal to c, where a, b, c are functions of x, y and u. And the initial conditions are x at 0s equal to x naught of s, y at 0s equal to y naught of s. Sorry, here there is a mistake. It is y at 0s. Okay, y at 0s is equal to y naught of s, u at 0s is equal to u naught of s. And the corresponding characteristic equations are xt is equal to a, yt is equal to b, ut equal to c. Now, the same system of ODEs can be written in the following way. So, we can write from here dy by dx also. Dy by dx is nothing but dy by dt into dt by dx. So, dy by dt is yt, the characteristic equation yt is b, and dt by dx is 1 by dx by dt. Dx by dt is a, so it is b by a. Similarly, du by dx is du by dt into dt by dx, so it is c by a. So this ODE can be written in the form, and this form is again similar to, now this is of the form a dy equal to b dx, and the second equation is c dx is equal to a du. Okay, so the ratios can be written like this. So from here dx by a is dy by b, and from here dx by a is du by c. So so we can equate these three ratios. So we have dx by a equal to dy by b equal to du by c. So in this way, here we are getting a system of ODEs. Here a, b, c are the coefficients. Okay, so we can write the ODEs as dx by a equal to dy by b equal to du by c. Now, we have to solve the first order system of ODEs in the yu plane, because we have y and u now, and we are considering x as a parameter. So here you can see, here you have y, dy by dx and du by dx. So we are dealing in the yu plane, and we are considering x as a parameter. Now Lagrange assumed that the two parameter set of solutions curves can be represented by the intersection of two families of integral surfaces. That is, as I told earlier, curves can be considered as a intersection of two integral surfaces. So he assumed that the solution of the above ODE can be represented by intersection of two surfaces, and the surfaces are psi of xuy equal to alpha, phi of xyu equal to beta. And the solution of the quasi-linear equation can be obtained as a function of psi and phi. Or we can write it as phi as a function of psi. Phi can be written as a function of psi. So this is a general form of this is a general solution of the quasi-linear PDE, that is f of psi comma phi equal to 0. Now this is the equation of surface. We will show that this can be written as psi of xyu equal to, we will get as a constant, which will be the solutions of the ODE, and can the general solution of the quasi-linear PDE can be written as a function of psi and phi, or we can write as phi as a function of psi. Both are same. In both way we can write like this. So a solution which contain arbitrary function is called an general solution of the PDE. Now how do we find this phi and psi? That we will see here. Now we have the surface psi equal to alpha and phi equal to beta are the surfaces, and we are assuming that it contains a characteristic curve. Let we denote the vector p by ABC. ABC are the direction ratio of the given problem, okay, which determines the characteristic curves. Now assume that, so we have p can be found from the problem, okay. Now we have to find two independent vector fields p1 and p2 such that they should be independent and they both should be orthogonal to p. P1 and P2 should be independent and both should be orthogonal to P. So orthogonal means their dot product should be 0. So P dot P1 should be 0 and P dot P2 should be 0. And which simply means that dot product 0 means what you have to do is AA1 plus BB1 plus CC1 equal to 0, AA2 plus BB2 plus CC2 equal to 0. Now we further assume that P1 and P2 are exact. P1 and P2 are exact. So I think this things you must have studied in vector analysis in your degree. Okay. Exact means their curl will be 0. Curl is nothing but del cross. So curl of P1 is 0, curl of P2 is 0. That is del cross P1 is 0, del cross P2 is 0. And hence we can find, since P1 and P2 are exact, there exists a scalar function phi whose gradient is psi. Okay, so there exists a scalar function phi whose gradient will be this vector field. This also you have studied in your degree class. Okay, it means that there exists two scalar functions psi and phi such that P1 equal to del psi and P2 equal to del phi. Del is a gradient. I will recall the value of del is nothing but it is a vector operator. It is I dou by dou x plus j dou by dou y plus k dou by dou z. It operates on scalar quantity, and del phi is nothing but I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. Del is gradient. Okay, so since P1 and P2 are exact, we can write corresponding to P1, we can find a scalar function psi whose gradient is P1. Since P2 is exact, we can find a scalar potential phi whose gradient is P2. Okay, these theories are all you have studied in your degree classes. And we have also studied the methods to find phi and psi. Here also we have to adopt those methods. We have to find psi and phi like this. And d psi, the total derivative of psi, is nothing but del psi dot p. So it is the derivative in the direction of p. Derivative of psi in the direction of the vector p is given by del psi dot p. But what is del psi? Del psi is nothing but p1. So it is p1 dot p. And what is p1 dot p? Since p1 is orthogonal to p, p1 dot p is 0. Similarly, d phi in the derivative in the direction of p is given by del phi dot p. And what is del phi? Del phi is p2. So it is p2 dot p. And since p2 and p are orthogonal, we get this is 0. So we get d psi equal to 0, d phi equal to 0. It means that psi is a constant and phi equal to constant on every characteristic curve. So psi and phi are constants on the characteristic curve. So here we will get, so earlier we have psi equal to alpha, phi equal to beta. We have the equation of the surfaces. Then you will get psi and phi as constant. So here you will get a relation between these two. Suppose psi equal to c1 and phi equal to c2. Then we have a relation f of c1 c2 equal to 0. and in this way you will get a general solution of the PDE. So if you do a problem, it will be more clear to you. Okay, so problem we will see in the next class.